Hello and welcome back to the Hyperthesis episode 12. Wow, we actually got to episode 12. It has been a while since once a week. So it's actually been like 3 months. It's good to be back, even though I'm a little tired today. I think most of us are quite exhausted. Nevertheless, my name is Pheely.
I'm Patrick.
I'm Liam.
So today we're going to be talking the main topic about one of the most fundamental substance to life on Earth, which is water. And water is very complicated, surprisingly, because we know it's at H2O. But to start with, we're going to start with the interesting topic that some of us has found. So take it away.
So the last time we recorded, directly afterwards, we were talking about ironing clothing because I had to iron some things. And it got us thinking. Pheely mentioned that we should maybe look into what's going on there. Why is it that you can... How do you remove these wrinkles from clothes and create creases? So I looked into it a little bit. So to keep us on the same page, ironing is using some heated tool, an iron, to remove wrinkles, create creases, and make your clothes look nicer. So it was called an iron because originally, back in the day, an iron was just a big hunk of cast iron metal that you would put in a furnace or put into a fire and then take out with a glove or a towel around your hand or something, and then you would push it into your clothes. It would remove the wrinkles. Sometimes you would add water to it to create steam, but we'll get into that. Usually, you need the iron to be around 180 to 220 degrees Celsius. In order to do anything. Different fabrics require different temperatures. Some of them require water, and we'll talk about that. Well, I'll talk about it a little bit, briefly. And I think the first known use of a heated iron was to have occurred in China, although I don't have a citation to back that up. I just read it online. So do your research. Don't believe me blindly. But the electric iron was invented in 1882. So, how does it work? What's going on? So, fabric, so the things your clothes are made of, and think of like cotton or wool, for example. I think that's the easiest one to think of. It's typically made of these long-chain polymer molecules that create these fibers in material. You have all these interweaving fibers, and some of them are bent and some of them are straight. And what you do when you iron them is you apply this heat at pressure, and it loosens the bonds in these long-chain polymers, and it heats them up. And while they're hot, and then the pressure kind of straightens them out. And then when they cool down, they reform in these kind of straightened patterns.
So I'm curious, does the iron straighten like the bonds, say, between two strands within there, or does it actually do something with the bonds within the super long molecule itself? Because I know wool or cotton, it's straightened, so they're all strands facing the same direction, and then they're twisted into each other to actually create thread or string or yarn. But is that iron straightening like and weakening, I guess, or relaxing the bonds between the different strands, or is it within one strand that the bonds are relaxed?
I think it's within the individual, like the polymer strands, and not so much. It doesn't like unwind the fibers, but it straightens out the polymer strands. So from a physics point of view, basically what's going on is a phase transition, a reversible one, and that's why you can iron things and remove wrinkles, but then reform them later.
Well, I don't know if the geometrical folding would be a real phase, or phase in terms of thermodynamic has very specific meaning, and you have to be very careful when you say phase transition. But since we are not writing a paper and not submitting to a journal, I think we should be fine. But if you're strict about it, don't come at us with axes. And also, this gonna be related to the main topic, which is we're gonna be talk about, because this happens a lot of times when we want to change material, right? Because material, when they're solid, like solid materials, they're configured in a certain structure, and to change that structure, well, you can mold it, you can basically force it to be something else, or you can heat it up so those structure breaks down into something else, maybe liquid, maybe a softer form, and then you recool it with certain speed of temperature. I think, some people would call it annealing. You see those in swords when you want to temper your sword and stuff. I think it's a similar concept and idea to the ironing we are talking about.
I think it's a little different, but I think it's kind of qualitatively similar. Although it's I don't know about when you forge a sword and temper it. Like I don't know if that's really reversible. I mean, I guess it is. You can grind the sword up and remake it, but this process is a reversible process, and it's also going to be related to water, which we're going to talk about because I'll come to that because adding water to the ironing process for certain materials makes it work better, essentially. So I'm not exactly sure if it's what. Yeah, I don't know if it's technically a phase transition, but it's some kind of it's called a glass transition. So from a physics point of view, most polymers, and including these ones which make up our clothing, have something known as a glass-liquid transition, or just a glass transition. So this is the gradual and reversible transition in an amorphous materials from a harder to a so-called glassy state, which is basically just a softer or looser, more viscous or rubbery, depending on your material state. So an amorphous solid is a solid, like a crystal, but it doesn't have that long range kind of crystalline order, they call it, which is basically symmetry. So when you look at a crystal, it has these kind of repeating patterns throughout it on a larger scale, but amorphous solids don't. And an example is glass, and that's why I think they call it a glass transition.
Yeah, I think for the most common and well-known example is sodium chloride, or as we know, it's the table salt. So if you look at the table salt, you can see it's a cube. Right? You pick a grain of salt, it's a cube. And the actual microscopic structure, or as we know, it's like the primitive cell or the cell, whatever, it's also a cube. So it's made up of stacked up cubes. So the microscopic structure that we see are cubes. And a lot of structures are like that. You look at quartz, a lot of crystal you see have some remnants of its microscopic structure in what we see, although may not be exact because there's a lot of other factors that separate the microscopic from macroscopic structure. Nevertheless, amorphous or glassy means there's no really microscopic crystalline structure. There's no little cubes in there. They're just kind of randomly distributed around.
I will just point out as a teaser for our main topic, snowflakes are also some sort of crystalline structure as well as different types of ice.
Exactly. Yeah, there's a link I have here for us. The viewer can't see it, unfortunately, but you can probably just Google amorphous structure or something like that online. But it's a nice picture of quartz versus quartz molecular structure versus glass. And the quartz are like these nice repeating patterns. And like you said, Pheely, that's idealized. In reality, in nature, there'll be small other kind of imperfections throughout, but you could create, in principle, like your salt, right? Like perfectly kind of these patterns are nice and symmetric and blah, blah, blah. However, amorphous solids aren't like that. They're kind of random. Like there might be some kind of structure, but it's not periodically repeating in a nice way. It kind of changes depending how it's anisotropic opposed to isotropic, say. So from a physics point of view, what you're doing when you iron is that when you raise the temperature of these polymer chains, you reach this so-called glass transition, where they're kind of you can change how they look. Sorry.
Yeah. So with this glass transition, before it's ironed and it's wrinkled, does it go through a reverse transition? So where it goes from this, I guess, solid, more cooled state in which it's actually an amorphous solid, and then when it gets wrinkled, there's some sort of application of pressure or increase in temperature that causes it, or is it kind of the equivalent of just breaking a pane of glass?
I have no idea. I guess it's like, what came first, the chicken or the egg? Did it start off in this glassy state, or did it start off in its regular state? It depends which way you go, if it was reversible or not, but I'm not sure. So, yeah, you raise the temperature with an iron of these long polymer chains. They go into their glassy state so that they can become softer and more malleable, say. But not it's not such they're not so loose that it becomes a liquid. That would be kind of weird if you put an iron on your pants and it just flowed all over your floor. So once the heat from the iron raises the temperature of the fabric, so say you're ironing a pair of pants, it will pass this. The polymer chains will pass this glass transition point. They'll gain some mobility so that the fabric can be shaped and flattened, and you can get rid of the wrinkles and create creases. And then you form it, and then you let it cool down, and then it will go back, but in the opposite direction over this transition, and it'll become back to its original state where it can note these polymer chains are now kind of stiffened up again, but now they're stiffened up due to the pressure of the iron you put onto it into a new shape, which is ideally flat and smooth looking. So they'll hold their shape once again.
Yeah, I mean, this sounds weird, right? Because if you think of like a rubber ball, if you squeeze it, it will just come back to its original state. But what we do here is to create a condition that makes the original state not preferable. So by applying pressure to it and keep the pressure on and lowering the temperature, you create an environment that the original wrinkly state do not want to exist anymore. So the more preferred state would be the ones that more neat and wrinkle free. So I think this idea, even though it sounds very common or normal in daily life, there's a lot of physics and science that go into it. Like even these days, people don't use real iron anymore. Some places use like a steamer, basically like a nozzle with steam, and just run through the fabric and just do the same thing. Because at the end of the day, it's not about having a piece of heated metal onto the fabric. It's about changing the state of the material to another one, and may go back to the ones that prettier for us.
Yeah, so it's not that your pair of pants prefers to be wrinkle free. I guess it's that when you put it in this heated state, the pressure is what changes the wrinkles to be removed. But yeah, it's I guess its preferred state is kind of equilibrium with your environment, right? So if you apply heat, it's gonna cool down.
Well, you have to think about what wrinkles come from too, right? It's come from all the external pressure when you use it, when you put it around. So it slowly creates these folding of molecules. It's actually people who study like knots, people who study protein folding to try to understand why things fold. And when you have like external pressure over a long period of time, it can actually create these creases and little folding molecules, which with time create all these kind of microscopic folding and creases.
Yeah, that's a good point. Like, you have a pair of pants on with a crease, and if you like sit down in them on top of the crease, it won't go out right away, but if you sit there for a few hours, it'll have more of an effect. And the other thing you said with the steam, that I can come to that point now. So what you said, they'll add steam instead of ironing, and they'll kind of like gravity straighten out these proteins instead. So the idea is that when you apply heat, you're reaching a certain temperature where this glassy transition occurs. But another way to do it is to add water. So by adding water, you actually lower the temperature that the water kind of has two effects. One of them is that it helps your hot material not burn the clothes. But if that were the only case, if that were the only thing that was happening, you wouldn't be removing wrinkles at all. They'd still be there because you would need a sufficient temperature to reach that transition point. However, by adding water, you actually lower that transition point so that you need less heat to reach it. And so you have like a steam button on an electric iron, or you have like this mist button that sprays out water. And that's kind of the purpose of that.
Well, think about it. To distribute heat into any kind of material is difficult, like, because if especially fabric, they're porous, they're They have holes everywhere. They're loosely bounded, and to actually distribute heat evenly, putting little. That's why we use the spray nozzle, right, to make like small particulates of water, and water really a decent heat conductor. So it's actually really useful to distribute heat.
Yeah, especially you can use the steam function. You get water coming out, but in its gaseous state, so it kind of like goes through all these holes in the fabric and gets around to all the polymers and whatnot. So it's quite useful to lower that transition temperature. And so, if, for example, I think like wool and cotton, that's a good thing to do. Well, I use it for wool when I iron. But yeah, there's other advances in ironing. So there's permanent press clothing, and I don't know the details of that, but maybe we can talk about that another time, where you don't really need to iron them as much, and they've probably figured out some way to keep these polymers straight for longer.
Well, I just want to add to before I came to Canada, we don't use dryer. So we don't use heated dryer like the tumbler. Well, we have them, but usually we just sun dry it, and usually clothes when you sun dry, they have wrinkles on them because it's not heated, right? You come out of the washer wet, and you just hang it up, and it helps with some creases because of the gravity. But we also have to almost iron everything. But here, I just put it in a dryer just because it has heat. If you take it out at the correct time and hang it when it's still hot, it actually get rid of a lot of wrinkles.
That actually you bringing up that point, I learned something in my head. So I was always told that if you have wrinkled clothing, you can just put it in the dryer, and you can take like a damp cloth or something and put it in the dryer with it. And I always thought, well, with an iron, I always thought it was the pressure that kind of removed the wrinkles and whatnot. But after kind of looking into this a bit, and you saying that, well, yeah, of course, putting the water in the dryer with it removes the wrinkles. It lowers the transition temperature. The heat added removes the wrinkles. And because it's not tumbling, it's not when it tumbles, it's not hitting the same kind of angles and the same spots every time. It effectively removes the wrinkles. And I think that's what's going on there, actually. So that's interesting.
Yeah, in physics term, I think these things, we just call it annealing. When you anneal a material, you heat it up, and you either slowly cool it, or you can cool it fast to create glass and stuff. But I think we can move on to the main topic, because I'll just briefly summarize this a bit. So we talk about ironing, and we find out that it's not as simple as it seems. That polymer has to go through some unfolding, and there's some kind of transition between different states that go into how we reconfigure the preferred configuration of those fabrics, which in a practical sense are pretty easy to do just by heating it using an iron. And we found out that water is actually a good heat conductor in terms of for fabric. So we use that to help fasten the process and protect the fabric itself. All right, so to move on to the main topic today. So topic today is on water. And water is such a fundamental molecule. Think about it, everybody know it, H2O. And I'll start with a little anecdote, but it's kind of scary a little bit when I was younger, because at the time there were those scam emails where they ask you, they're like fake news and stuff, make you scared and make you share it. And there was this one that at the time I knew science, so it's kind of funny. There was this toxic material that was released years. That was like, wow, it's on the news. The statistics were actually correct. It's called dihydrogen monoxide. And this material, if you inhale it, you die. Thousands of people in the world die from it every year. If you consume too much of it, you die. If you get into your eyes, it hurts. The purest form of it, you can't even consume it safely. You got into your ears, clog your ears. And there was this statistic that just from, it sounds scary, dihydrogen monoxide, which turned out to be two hydrogen attached to an oxygen, which is water. So people dry out every year. People consume too much water, their cell got bloated. You can't inhale water because you would die. So those statistics are factually correct, but it's presented in a way that makes people scared. They just realize that, well, it's actually water. And the water has interesting property because H2O, you think the molecule would stay in a straight line, just come on, two hydrogen and oxygen in the middle, easy. But somehow it actually have a bent structure where it has a 104.5 degrees angle between them. Well, the chemists will explain it with the valence electron or the lack of it. And yeah, there's some things I'm not quite sure. I'm sure if we just solve some Schrödinger's equation, we can see those clouds and plot out the probability. Well, yeah, I think you can look it up, but sure.
Yeah, all of chemistry is just a Schrödinger equation, right?
Whoa, hold your horses.
But it's something to do with the fact that an oxygen atom has two pairs of valence electrons. Tell me if I'm wrong here. My chemistry is bad. It's been since high school since I thought about it. But each hydrogen atom, proton, neutron, and electron, forms a covalent bond with one of these two pairs from the oxygen atom. Anyway, each of these hydrogen atoms forms a covalent bond with the oxygen atom. And what ends up happening is that the electrons, each of the electrons, the one electron from the one hydrogen atom and the one electron from the other, they end up spending more time closer to the oxygen atom. And due to the protons in the hydrogen atom, you get this kind of polarity. So one end of the water molecule, the H2O molecule, is more electrically positive than the other. And I think it's the end with the two hydrogen atoms is more positive, and the end closer to the oxygen atom is more negative. So you get this polarity, and it bends the two hydrogen atoms towards each other at a 104.45 degree angle or something like that. And that is what makes water this miracle molecule. Even though we see it every day, we need it to survive. As far as we're aware, life needs water. It rains down on us. Most of our Earth is covered in it. We use it for everything. We use it for ironing. It's still this molecule that's very unique, and we don't really. There's a lot we don't understand about it. Although there is a lot we do understand about it.
Yeah, that polarity factor of water. So the fact that one end is slightly positive, and then, or two ends, like the two edges of it, are slightly positive, and then the center is kind of slightly negative. That, I think, is one of the most impactful and defining features of water. So because of that polarity, it likes to attract things and to essentially pull things along with it through some electrostatic attraction. And so, for example, if you look at the Grand Canyon, that was formed by water eroding, and water is known as the great eroder. And that's just because of water being slightly polar in one way or the other, and then attracting these different molecules. And the shape of water is also pretty important, not so much when it's liquid, because we don't get to see the effects of that somewhat triangular shape of water, but when it turns into different solids, we really get to see just the massive effect that slight bend in the molecule has on many different things.
Yeah, I mean, I thought when you said the shape of water, I was thinking to say, oh, water is a movie by Del Toro. Heard it's a good movie, won Oscar. But yeah, I was going to add on the Liam a bit. Well, it has two pairs, but not just normal two pairs. There's the two lone pairs. You think of it has 8 electrons, right? It's 1s2, 2s2, 2p4. So in p4 orbital, it fills the first two up and down, and then up, right? So you have two lone pairs. So it can make 2 full bonds with. It can take 2 more electrons. In group 6, or some people think it's 16. So it can take 2 more electrons to fill the orbital p.
Yeah, the
p orbital
bond. It takes the hydrogen electron.
Exactly. Yeah, so having those lone pairs on one side actually push the electronically, actually not like electrically push the molecules in certain bend. And to add on that, it's not just water that has this bent structure. The outer one is silicon dioxide, which is yeah. So it's SiO2, which also have this kind of structure. And people who study water molecular structure and its property look at silicon dioxide, that is basically brother, sister, neighbor, whatever, that have really similar behavior and state and phase transition and whatnot.
So in principle, if you had a river flowing of some non-polarized molecule, would it erode the river? Probably a tiny amount, but not as much as water. Because I guess you would get maybe erosion from things like atoms kind of quote unquote bumping into each other, but you don't get the polarity of a water molecule kind of pulling other molecules along with it, I guess. I don't know.
Well, you're talking about friction, like mechanical or erosion, right? I remember studying earth science, and I was like, well, a lot of things can erode just from friction, right? Just hitting molecules. Some of them get knocked away, but it's really slow. But what water does, since it's polar, it's a chemical reaction, right? That it binds to other things, so that's different. That's why, like, with how they create rust, right? Water, the oxygen molecules actually bind into iron. If you talk about iron, like it's create like iron oxide, which is known as rust. It actually takes away the iron, create the oxide. That's why when you have rust, you actually gain mass, you gain weight. Because it creates this oxide, you have gain more oxygen onto it. So yeah, it's chemical.
Just to put some names to it, so it's mechanical erosion versus chemical erosion. So things like the wind, that does a lot of mechanical erosion. So if you want rounded mountaintops over millions of years, that's wind. Whereas water is very, very chemically active in the sense where it is able to bind to things. And like you mentioned earlier, things dissolve easily in water, like salt and other types of minerals and just general salts.
Yeah, so the fact water's a good solvent is due to this kind of polarity. It has this bent shape, and most of its, I think, if like most of its unique properties are because of that. So it can even in living things, it's a solvent for polar molecules. So ions and proteins in a cell, for example, they're dissolved by water within the cell because it comes in and it kind of pulls things out.
Yeah, another fascinating property of water is the fact that it has a high heat capacity. Now, I'm not sure if that directly has to relate to its polarity and its shape, but the fact that water takes a lot to actually heat up. So if you've ever had to boil a pot of water for a cup of tea, then it takes a fair amount of time to actually boil that water. And it takes even longer to evaporate all that water, if you forget the kettle, to transition from, say, a liquid to a gas. And so this high heat capacity is very important for life in general because it helps with temperature regulation. So as was mentioned earlier in ironing, water can help to not increase the temperature too rapidly. So since it takes a lot of energy, for example, to boil, to go from liquid to a gas, that means it kind of acts as a buffer with that heat where it absorbs a lot of heat before that can be easily transferred to another surface. So that high heat capacity is also important for a lot of atmospheric and weather-related things.
Yeah, for those who don't know, heat capacity, I can't remember if you said it, but it's basically how much energy it takes to change the temperature of something. So water is a very high heat capacity, so it takes a lot of energy to boil it, like you said. It takes a lot of energy. It takes longer for it to cool down, stuff like that. And that's, yeah, exactly what you said. It has all these environmental effects. Like if you live along the ocean side, you tend to live in a kind of more chill climate in the sense that temperature wise, maybe not like weather wise, but temperature wise, it doesn't get as hot and it doesn't get as cold. as say if it's getting colder out, the water will stay warmer longer than the air does.
A cool little comparison I like to do with students is saying, okay, if you take say, just a sheet of metal or a car or a pop can or whatever, and you take it outside in the middle of the winter. So for people living in Canada, you know what winter is like. We can get down to -40 or -50 degrees Celsius. If you take that can of aluminum out, then it's going to get cold pretty quickly. Whereas if you instead fill that can of aluminum with coffee or like boiling hot water, it takes a lot longer to cool down. And that's a nice comparison of heat capacities. So aluminum has a very small heat capacity. Doesn't take a lot of energy to change its temperature, whereas water, as we said, does take a lot of energy.
I think that's also kind of why. So let's say you put in like, a pizza pocket into the microwave or something. The inside has all this sauce and pepperoni or whatever, and the outside's covered in like some doughy bread stuff. I don't know what it's called. So the very, very rough way, hand wavy explanation of a microwave is that it shoots out these little beams of light, these microwaves. We can't see them, but they're light. And the wavelength of this light is kind of around the same wavelength as these water molecules. And they basically just make all the water molecules in your food jiggle, and that increases the temperature. So when you shoot your microwaves through a hot pocket where the inside is made out of this water-based pepperoni pizza sauce or whatever, and the outside doesn't have as much water in it, you can touch it and it doesn't feel near as hot as the inside is. That's because the microwaves have interacted with the inside more and not the outside as much, and the inside will stay hot for a much longer time than the outside will. You take it out of the microwave, you put it on your plate, you touch it, you say, oh, that's fine, then you bite into it, next thing you know, your taste buds are melting off. So that's kind of another neat explanation as something that water is important in. And I'm sure there's other molecules that microwaves interact with a bit, but water is kind of the big one in food.
Yeah, water is somehow one of the most anomalous material we have, where things are counterintuitive that don't make much sense in such a simple molecules. I think there are more than 40 anomalies that we put down. It's like, but think about it, like water actually has, like, compared to any other molecules with the same size, with the same type of bond, water has like unusually high melting point, boiling point, critical point, surface tension, viscosity. Everything was just strange. And to think about it, ice, when you compress it, it melts. But you think about it, when you compress solid, it should get tighter, denser, right? It should stay solid, but ice melts. And also, like, hot water freezes faster than cold water. I think that was a little bit controversial, but there's some evidence on that. I think it's called like a Mpemba effect. And also, like, fish can live under the lake because the cold water, there's a warmer water at 4 degrees. At 4 degrees denser than the water at like 1 degrees or near freezing point. And that is counterintuitive, because when you think about something that is cold, you think about the molecules being closer together because, they're not moving as fast. So they're cold, so they should be denser. But water is less dense when it's cold in that specific region. And a lot of these can be explained through metastable states, which we may get into.
Yeah, and I think what I find really interesting about that is how kind of nature evolved around that. So the fact that this water molecule is bent and all these really weird counterintuitive properties it has, a lot of nature kind of exploits it. Like I said, in your cells, water is a good solvent, so it takes things in and out of them. Even the surface area of it, right? Like, it has a strong surface area. And again, that comes down to this polarization, the kind of boundary of the water. You get all these water molecules that kind of polarize and link together, but near the edge, they stop. So because of that, the surface tension is quite strong and it pulls inwards. And that's why you can put a drop of water on the wall and it just sits there. It doesn't kind of disperse and just go everywhere, right? So, one cool example of that is that's how trees work, right? Like, trees kind of siphon water up them all the way against gravity, all up into their branches and leaves and whatnot. And the surface tension of the water plays a big role in that. And like you said, a very interesting property is that as the temperature increases and water becomes ice, it actually gets less dense as it freezes, forms this crystalline structure, but it actually spaces the molecules further apart as it does that. Water expands as it freezes. That's why, at least in Canada, when the roads tend to crack, water gets in them, and then it freezes. It will suddenly become cold, and it'll kind of force the concrete or cement or asphalt or whatever apart. It has these very interesting properties, and even in like I said, or what I think what Patrick's or one of you said it, how ice will freeze in the winter, and it's less dense, so it floats on top of the water of a lake. And the warmer water will be at the bottom, and all the animals will kind of sit down there in their hibernation. They won't freeze because the ice floats to the top because it's less dense. So nature's kind of built around this funny little bent single molecule that's just everywhere.
It's very interesting to read about what's going on with how life forms and like how the ocean behaves, because we talk in the realm of climate change, we talk about rising ocean temperatures, but realistically that's only the first little bit of ocean near the top. Most of it is 4 degrees Celsius. It might change a little bit because you have an increasing pressure the deeper you go, but on average, excluding like the top, I believe it's less than a kilometer of water, much less than a kilometer, it's 4 degrees Celsius. And this is also another neat thing about water being the most dense at 4 degrees Celsius is that Lake Superior, which is kind of close to you guys, is also at that temperature, but it's also really good at preserving old stuff. So their shipwrecks are perfectly preserved in these cold water regions. And the fact that it's also fresh water helps. But yeah, just a fun little thing. And then the fact that water is so conducive to life, so when it freezes, there's stuff underneath that's still living because it doesn't freeze all the way, is what's motivating a lot of searches within and with outside of our solar system for life is water, because water is, from what we understand from our sample size of 1, it's necessary for life. Another cool thing about water, we're talking about it, ice being able to float on its, I guess a solid being able to float on its own liquid, is the existence of different types of water. Now, this isn't like salt water or fresh water, but heavy water. So heavy water exists as a, I guess you could say, molecular isotope. I'm not quite sure the proper term, but heavy water contains deuterium, which is heavier hydrogen because it has an extra neutron in there. And it has a lot of interesting properties.
Well, I think, when we say it's like, when I say it is anomalous, right? Water is an anomaly. Like it is, because if you think of any other liquids, if you melt down any other material like metal, molten metal, they behave like you expect them to behave. You pick other liquids that don't involve water. If you compress it, it gets smaller. If you heat it, it expands. If you cool it, it gets denser. But water doesn't. I just want to, emphasize on that too. And a little note is that 4 degrees Celsius is usually the temperature of your refrigerator. So that's why it can preserve so well. It's 4 degrees, 3 or 4 degrees, depends on your settings, because your freezer, of course, is negative something, right? Because it had to freeze. And other funny note is that water has more than 17 different crystalline phases where, they have ice 1, ice 2, ice 3. The most common ice that we see or we know in daily life is a hexagonal ice, where the microscopic cell structure is a hexagonal. It's hexagonal. So yeah, that's what we see in the fresh and whatnot. But that's not all it is. There's so many phases of ice. Like ice in space is different. It doesn't have the same structure as ice on on Earth. I think it was accidentally found in a lab somewhere, if I remember correctly. My former supervisor used to tell me that story, but some guy just left some drink or some lab thing on the table, and he found like, well, that ice looks weird, and he actually do some lab tests on the maybe X-ray diffraction to see the structure. Like, well, that's not the normal crystalline ice that we found. It's actually amorphous ice, which is a glassy ice that doesn't have any crystal structure but still remains solid. And that's the ice we actually found in space. Because think about in space, the water molecules are scarce. So when you want to form ice, it's like it takes a long time. So each molecule has to hit one another in space and collect those molecules to create this ice. So they don't have the time or like the amount of substance to create crystalline structure. So they are amorphous.
Yeah, and there's different other kinds of ice. I don't know them off the top of my head, but I remember when we were undergrads, one of our old physics prof went off on them one day talking about how there was like, for some reason I remember this number 7 or 9. At least there were 7 or 9 types of ice that he cared about in his research. I'm sure there's probably more, like this amorphous one you're saying. My question is that does this heavy water, does it behave in so this bent shape of typical water molecules? I'm assuming you'd still get that in heavy water because your charge isn't changing. You still probably get this polarity, just your mass is changing by 2 neutrons, I guess. So I'm assuming a lot of the properties that water has, this heavy water shares, but I'm not sure.
Well, the heavy water, because it's nuclear, right? It's not about valence electron effect. So I don't think it affects much in terms of the chemical reactions. That's why isotopes behave chemically the same or equivalent, because, well, chemical reactions don't take place in the nucleus. It take place on electrons surrounding it. So, I think that's the idea. But it's useful in nuclear stuff because you have a bigger nucleus, a bigger, well, I don't want to say bigger atom, but bigger nucleus. So people use heavy water to basically help stabilize a nuclear reactor and whatnot.
So I know heavy water is used in particle detection. So Patrick, can you explain that potentially?
Yeah, so heavy water is special because of the fact that it has an extra neutron in each of the hydrogens. So with just a hydrogen atom, you just have a proton and then an electron orbiting it, which makes it really ideal for bonding with, for example, oxygen to make water. Now, deuterium, which is that proton but with an added neutron in the nucleus, with still one electron orbiting, essentially doubles the weight of the atom. And with doubling the weight, you double the mass, and you are looking at a really effective but easy to, I guess, obtain material that's good for detecting. So we could technically use water for different types of particle detectors, but the fact that there's a neutron and there's a fairly high density of neutrons in just heavy water. So if you just had a glass of heavy water, that allows for a higher probability of particle interactions with those neutrons. And so you get a higher chance of recording something. So for example, the Sudbury Neutrino Observatory, the original detector there in Snow Lab, used heavy water. And I think it was insured for like $1 million or something. So it's not necessarily easy to come by, but it's easier than other substances.
Yeah, I remember some statistic, and I don't remember it, I guess, because I don't remember what percentage. But I heard that detector that Arthur McDonald won his Nobel Prize for contained like most of the world's heavy water or something like that in it. But we are slowly running out of time, So I think we should wrap things up.
Yeah, I think that heavy water that they had, because the US couldn't just give Canada for free, right? Because it's actually like a sensitive material. I think they lent it or sold it like to us for like $1 or something ridiculous.
Yeah, it's rented essentially for $1. I will just add one final thing about heavy water, and that's really good at capturing other neutrons. And so that's why it's used in nuclear reactors and different types of very neutron intensive processes like splitting up uranium. And that's also why it's challenging to come by and is kind of a protected substance, because if you're using heavy water, chances are it's going to be for a nuclear reactor or a physics experiment.
Or nuclear weapons. Well, yeah, I want to add at the end, because I feel like I used to study water in terms of research, and there's so much I haven't talked about. A lot of phase transition, metastable states, different types of transitions that are useful in submarines. Some are related to top secret propellers and whatnot. And there's so much more about water that people don't know about or aren't aware of. There are actually conferences in Europe just on water. And it's like, everybody publish about water because chemists interested about it, engineers are interested about it, physicists are interested about it. Like everybody is affected by water at any point. It's in their life. So the research is very, very hot topic. Nevertheless, we're going to get to the part of the story. Before that, I will get Patrick to let you guys know how to contact us.
Right. So we are always interested in hearing your thoughts about our show. So you can find the show on Spotify. We are hosted on anchor.fm/hyperthesis. So that's our base, but we are found where most places where you can find podcasts, in particular Google Podcast and Apple Podcast. And I would highly encourage you to leave us a review on any of those services, or feel free to send us a message or email. You can email us at hyperthesispodcast@gmail.com, or you can find us on Instagram at the Hyperthesis. So make sure to reach out to us if you're interested. And we're also always interested in hearing about other people's different research area, and would love to have other guests on the show, as you listened to in the last episode. So please reach out to us, give us a listen, and share us wherever you can.
All right, so the story today is a bit scuffed. Nevertheless, it's about a great man who, well, since you're listening to this, you actually use one of his algorithm at some point, and he's just such a cornerstone, or like at a pivotal moment of computer science and mathematics. So this is the story of Leslie Lamport. So he's a computer scientist. He worked for Microsoft, actually. So at the time when he was a computer scientist, well, he is still, but computer scientists weren't a thing. So computers just started. So I actually know him a bit. Well, not personally. I heard of his name because we use LaTeX. He's the forefather of LaTeX, who actually made it from text. Well, to get into it, so there was this quote that I really like when I listened to his interview, that he said, coding is to programming what typing is to writing.
For those who don't know, LaTeX is this program that a lot of scientists, mainly physicists and mathematicians and chemists, use to write their publications or books or whatever.
Spoiler alert. Yeah, so he explained that coding, is just a way to express things. So you wouldn't teach people how to write by teaching them how to type, right? Like, writing is about expression of ideas. It's about the mental engagement of the idea and explain it into words. But the act of typing is just, to basically physicalize it out. So in terms of coding, it's the same thing. The underlying programming is not about the code. It's about the idea behind it. is about the algorithm. And what are algorithms? Algorithms are mathematics. And I think that he said it's like, well, if they're just writing codes out, they're just, they're like hypotheses. They're just conjectures. If they don't prove it using mathematical theory, using mathematics, they're not theorems, they're just conjectures, and they might not work really well. So Leslie Lamport, after graduating with PhD in math at Brandeis University in 1972, so Lamport worked as a computer scientist at Massachusetts Computer Associates from 1970 to 1977 at the SRI International. And at the SRI International from 77 to 85. And later on at the Auto Corporations, and then he joined Microsoft research team in Mountain View, California in 2001 and spent all his time since then. And his research is actually close to what I used to study for my master's, which is distributed system. So he's actually like a pioneer who started just from kind of like an accident. So when he spent his research career, he was doing industrial research. And, he actually liked industrial research because, according to him, if you just be by yourself and you come up with problems, there are only few things you can come up with. But if you go out in the world, you can see that a lot of people are working on real systems, real problems. There are millions of problems out there, and you can look back up your work on, and then you can come up with the more, other real world problems. So when he started back in time in 1974, so he was busy at a local neighborhood bakery, and he noticed that the bakery has several cashiers. But if more than one person approached a single cashier at the same time, the cashier would try to talk to all of them at once and become confused. Makes so much sense. So he realized that there needed to be some way to guarantee that people approach cashiers one at a time. So this problem reminded him of an issue which had been posed in an early article by a computer scientist, Esker Gistar. So another issue, like how to share dinner utensils around a dining table. It sounds like a simple problem. So one of the coordination challenges was to guarantee that each utensil was used by at most one diner at a time, which became to be generalized as the mutual exclusion principle. So basically the same challenge that Lamport faced at the bakery. So in one morning, an idea came to him on how the bakery's customers could solve this mutual exclusion among themselves without relying on the bakery. So the bakery doesn't have to do anything. So roughly it's like this. So people choose a number when they enter the bakery, and then they get served at the cashier according to the number ordering. To choose a number, customer asks for the number of everyone around them and choose a number higher than all the others. So this kind of start to make more sense in terms of algorithm that we see when we queue for something in computers, right? You get a queue number, you get all these stuff. So it's actually lay foundation of how systems talk to one another and who should contact the server first. So this simple idea became an algorithm for solving the mutual exclusion problem without requiring any lower level indivisible operations. So no operations. So it's like a source for many other ideas, the other derivative ideas that came out for the issues. So for example, like some bakery customer, what if they take a long time to check the order's number? So what if more customers arrived and selected more numbers? So what if we have a manager to have a snapshot of all customers' number to prepare pastries? So like Lamport later said that for a couple of years after my discovery of the bakery algorithm, is what he called it, everything I learned about the concurrency came from studying it. So this bakery algorithm became one of Lamport's pioneering works. It's actually a nice, amusing name too. So it becomes one of the main pillars of computer science. And these collections of papers, has so many. You can check it out at his homepage. That I think it's like 190 papers on multiple algorithm and the development of algorithm. And yeah, he has many, like a plethora of impactful papers that you can read. And he basically created an entire community of computer science that use mathematics to solve problems. So an author outside of these algorithm and mathematics, computer science-ish, so he developed what we scientists, a lot of scientists use as LaTeX. So actually we have something called TeX, it was developed by Donald Knuth. So TeX was a typesetting language to type complex mathematical expression. However, it's difficult to use. It's actually very complicated. You have to write your own subroutines, a lot of code to just write a simple equation. So it's a good typesetting, but it's complicated. So even though Lamport didn't really create these ideas, but he really pushed the system of text so far. So he created these macros, which are a set of commands that improve the quality of life of text, that makes it flexible, makes it accessible to new people, and much, much, much easier to use. And once he developed it, it became a de facto standard for publishing in computer science and physics and many other fields. So, and as scientists, I use LaTeX right now. Since I'm trying to get a publication, I use it every day. I stare at LaTeX. I know a lot of commands. I even try to make posters, presentations and stuff using LaTeX. I draw pictures in LaTeX. I try to do musical notations in LaTeX, which you can. There's a lot of things you can do in LaTeX, and they do it beautifully. And it's not something that, type and see like Microsoft Word. You get what you type, you get what you see. You type in, that's what the document looks like, allegedly. Not usually when you send it around, it doesn't look like, what's on the Word document anymore. But LaTeX, you see a bunch of weird code, and then you compile it to get the nice, beautiful document out. So, yeah. So this is a story of Leslie Lamport. So anytime you access a modern computer, so you are likely to be impacted by his algorithms. So, and all this work started with the quest to understand how to organize a queue at a local bakery. And that was a quote from the award he got. So, with that, I hope everyone enjoy, and we'll see you next week.
Bye, everyone.
See ya.